everyone, this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. So welcome to this lecture. In this lecture, we'll discuss about the number system and number-based conversions. What are the various types of number systems we have, and what are the techniques to convert a number from one number system to the other number system, we'll see. So before entering into the topic, first let us see what is a signal and what are the different types of signals. Those are what do you mean by analog signal and digital signal, and what is digital electronics, and what are the various number systems we have, so that we will see in this lecture. So first of all, what is a signal? Signal is a function of one or more independent variables which contain some information. So whatever the signal which is a function of one or more variable and which carries some information is known as signal. So here some examples of signals: voice signal, video signal, and even we will talk in phones, like telephones will talk. So that telephone wires will also carry some signals. So that is also an example of signal here. So again, we can classify the signals into two types. What are the two types of signals? Those are analog signals and digital signals. So what do you mean by analog signal and digital signal? An analog signal is continuous signal in which the time varying quantity represents another time based variable. In other words, one variable is analog of the other. So that means analog, in simpler way, we can define an analog signal as a continuous signal which varies continuously with respect to time. So analog indicates continuous. So that is analog signal. Coming to the digital signal. So continuous signal, some example I will give you, that is analog signal. So the sinusoidal signal is the best example of an analog signal. So here on the x-axis always we take time period, and on the y-axis we will always take magnitude. The magnitude may be either voltage or current. So the magnitude is varying continuously with respect to time. So that is what this is called as analog signal, or else it is a continuous signal. Coming to the digital signal. What is a digital signal? So digital signal is the signal that represents data as a sequence of discrete values. Majorly the discrete values are 0 and 1. So that means the data will be varying as a sequence of zeros and ones. So here the thing is, in this case, the time period as well as the amplitude will be discrete in nature. Whereas in analog signal, the time period and amplitude both are continuous in nature. So here, with the digital signals, the physical quantity representing the information, that is the things, variable electric circuit current, or voltage. So always you remember, in a simpler way, digital signal is a signal which represents a data as a sequence of discrete values, and the discrete values are always zeros and ones. Okay. So now coming to the digital circuit. So what is a digital circuit? So whatever the thing that we are learning now, that is a number system, these are very basic things that we need to know when we are going for the digital circuits. So a digital circuit is a circuit where a signal must be one of the two discrete levels, and each level is interpreted as one of the two different states, that is either on or off state, or 0 or 1, or true or false. That means the two discrete values of a digital signal can be represented either on or off, 0 or 1, or true or false. So digital circuits are the circuits which process the digital data. So that thing you have to remember. So the examples of digital circuits are so many things we have, like adders, the subtractors, multipliers, and even counters, registers, and multiplexers, encoders, decoders. These are all the digital circuits which can process the data, that is digital data, which is in the form of zeros and ones. So that means in this circuits use transistors. Again, the basics for this for building this digital circuits are again the transistors. So the transistors are used to create logic gates in order to perform Boolean logic. And basic logic gates, we have so many logic gates like AND gate, which we'll be studying, AND gate, or OR gate, NAND gate, NOR gate, XOR and XNOR. So these are all the logic gates. How these logic gates are implemented? Again, using the transistors, diodes and resistors. So the transistors are major blocks which are used to implement the logic gates in order to perform Boolean logic. So this is about digital circuits. And what is digital electronics? So digital electronics are those electronic systems that use a digital signal instead of an analog signal. So the digital electrons are most common representation of Boolean algebra and are the basis of all digital circuits for computers, mobile phones, and numerous other consumer applications. So wherever we are using in a household, so everything comes under digital electronics. And this could include even laptops and televisions, remote controls, and other entertainment systems. And even we can have kitchen appliances like dishwashers, washing machines. These are all will come under digital electronics, where they use digital signal instead of an analog signal. So the computers are one of the most complex example and will make use of numerous complex circuits. So these will be using various circuits, complex circuits. So the fundamentals of digital systems and logic families. So the digital signals, digital circuits. So these are the fundamentals here. So next we will now enter into the number systems. Before that, we'll enter into the number systems. So what are the number system? So number system is a way of representing a number or else representing any information. So we have various number systems here. Those are decimal number system, binary number system, octal number system, hexadecimal number system. So here these are mainly classified based on the radix value. Based on the radix value, we can represent any number in different number systems. So here the value representing a particular number system is called as radix or base. That means each of these number systems will have different value of R, and R is known as radix. Okay. So if the base of a number system is R, then the numbers present in that number system are ranging from 0 to R minus 1. So for example, R may be any number. So that means based on the value of R, we can classify the number systems. Okay. So for example, if R is equals to 2, the number of symbols that can be included or else number of digits that can be included in this number system may be 2. And what are the symbols that are included here? 0 to R minus 1. So if R is 2 here, so what are the symbols that are included in number system with base R is equals to 2? 0, 1. For example, if R is equals to 4, that means if radix of a number system is 4, then what are the numbers that may be included? 0 to 4 minus 1, that is 0, 1, 2, 3. These are the symbols that are included in a number system which is having a radix of 4. For example, if we have R is equals to 10, then the numbers that can be included or else the symbols that can be included in this number system will vary from 0 to R minus 1, where R is 10, 10 minus 1 is 9. So 0 to 9 are the symbols. Totally, how many symbols we have? 10 symbols we have. So that means in any number system with base R is equals to, with base R radix is equals to R, then that number system will include numbers or else the numbers present in that number system are ranging from 0 to R minus 1, and the total number of symbols present in that number system is equals to R. So that is about the number system. So now first let us see the decimal number system. What is a decimal number system? So the base or radix of a number system is 10. Then that type of number system is known as decimal number system. That means if R is equals to 10, then that number system is said to be decimal number systems. So that the number of the numbers ranging from 0 to 9 and are used in the decimal number system. That means 0 to 9 are the symbols that are used in the decimal number system. So totally how many symbols here from 0 to 9? Totally we have 10. That means what I want to say, the symbols or else the numbers, digits or else the digits present in a number system is equals to the base R. Okay. So now the part of the number that lies to the left of the decimal point is known as integer part. As you all know, decimal number can be represented like 123.25. So we have a point here as it is a decimal number system. So we always call this point as decimal point. And to the left side, whatever the number we have, it is the integer part. It shows the integer part. Whereas the digits that are lying on the right side of the decimal point will represent the fractional part. Okay, so this is the number system, decimal number system. So decimal number system is a system in which the base R is equals to 10, where it includes the numbers from 0 to 9. That means the total number of symbols or digits present in decimal number system are 10. And here the example of this decimal number system is this one. So whatever the symbols that are lying in the range 0 to 9 will constitute a decimal number. So whenever you are representing a decimal number, you should represent, by default also it will be considered as decimal, even if you can also represent with a base 10. Base is always represented as a subscript. Even we can also have fractional number also, 13.58.625. This is also a number which can be considered as a decimal number. Now coming to the okay, so here and one more thing we have to remember, that in a decimal number system, as the bases are, each digit in the decimal number system will have a positional weight which is of the powers of 10. So each digit in the decimal number system will have a weight which is of the power, which is represented as the power of 10. So here now, for example, we have 1358. So how can we represent these positions here? This is in the 0th position, 1, 2, 3. Always the position starts from 0 to R minus 1. So 0, 1, 2, 3. So the positional weight of this one is 10 power 0, and this is 10 power 1, and this is 10 power 2, and this is 10 power 3. So that is, how can I write this one? I can write this one. These are all the things that you have learned in your school level. So I can write this one as, just a second, 10 power 3 into 1 plus 10 power 2 into 3 plus 10 into 5 plus 8 into 10 power 0. 10 power 1, 10 power 0. So how much it is? 10 power 3 means 1000 plus 10 power 2 means 100 into 3, that is 300, plus 10 into 5, which is 50, plus 8. Totally, what is the number here? 1358. This is the representation of decimal number with the help of positional weights. Now, for example, let us consider I have a number 1358.625. So before the decimal point, the positions will start from 0, 1, 2, 3. Whereas after the decimal point, that is to the right side of the decimal point, the positions will start from -1, -2, -3, and so on. Now, how can I represent this one? So it can be represented as again 10 power 3 into 1 plus 3 into 10 square plus 5 into 10 plus 8 into 10 power 0 plus 6 into 10 to the power of -1 plus 2 into 10 to the power of -2 plus 5 into 10 to the power of -3. Now what is the value we are getting here? 1000 plus 300 plus 50 plus 8 plus 6 by 10. 6 by 10, how much we will get? 0.6. 2 by 10, 2 by 100. 10 power minus 2 is 1 by 100, right? So here, how much? 2 into 2 divided by 100, which is nothing but 0.02, plus this one you will be getting it as 0.005. If I add all this, I'll get the same number, 1358.625. So this is how we can represent a decimal number. So that means the positions of a digit from to the left side of the decimal point will start from 0, 1, 2, 3 and so on. Whereas to the right side of decimal point, the positions will be starting from -1, -2, -3 and so on. So like that, we can represent a number, decimal number, as in terms of powers of 10, like this. Okay, next, binary number system. So here, binary number system, where the number system in which the base or radix is equals to 2 is known as binary number systems. So as base or radix is equals to 2, what are the symbols that are included in the binary number system? That ranges from 0 to r minus 1, where r is equals to 2 in a binary number system. So that means the symbols that are included in binary number system are 0 and 1. So 0 and 1 are the two digits that are used in the binary number system. That means whatever the number that you are going to construct using binary number system will consist of only two symbols, 0 and 1. And this is also called as base 2 number system. And each position in a binary number represent a 0 power of the base 2. Represent a 0 power of the base 2. Example, 2 power 0. The last position in a binary number represent an x power of the base 2. So example, 2 power x, where x represents the last position, 1. So here, that means here in case of decimal number system, what we have considered, each digit has a positional weight and it is expressed as powers of 10. Whereas in binary number system, each digit again has a positional weight where it is expressed as power of 2. So for example, we have a binary number 1101. So this is a binary number. So always the binary numbers are represented with radix or else base 2. So here, when I have a number with this kind of sim representation, that is base 2, we can identify that as a binary number, right? So now how can I represent this one? So I can represent this as the positional weights are always starts from 0, 1, 2, 3. So here, this I can write it as 1 into 2 power 3. And as I already told you that each bit position, each digit will have a positional weight in the powers of 2. What is the position here? 3. So that is why the weight of this bit is 2 power 3 plus 2 power 2 into 1 plus 0 into 2 power 1 plus 1 into 2 power 0. So these are the positional weights. Okay, so that is about the binary number system. So even we can have a binary point also, that is 1101.111. So it is binary point. But as why we are calling it as binary point? Because this is a binary number where this point is also called as binary point. To the right side, the weights will be, or else the positions will be varying from 0, 1, 2, 3 and so on. Where to the left, to the right side of binary point, again the positions will be changing from -1, -2, -3. So whatever the number which includes only ones and zeros is said to be a binary number. So no other symbols are allowed in the binary number systems. Now coming to the octal. So as the name itself indicating octal. Octal means what? R is equals to 8. What is R here? Radix or base. The radix or base of our octal number system is 8, where the numbers that are included in octal number system is 0 to r minus 1, where r minus 1 is nothing but 7, that is 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. So these are the numbers that are included in octal number system. Okay, so for example, I have a number. So that means any octal number should have only the digits from 0 to 7. So if you have any if you have a number with 9, then it will not at all be an octal number. Okay, so that is the meaning of symbols in a number system. So coming to the octal number system, it is having 8 digits. Those are 0, 1, 2, 3 and so on. 7. It is also called as base 8 number system, and each position in an octal number system is having a positional weight in the power of 8. Okay, and one more thing. So here we have to remember the leftmost digit in any number system is called as most significant bit. Most significant bit, or MSB, most significant bit. Why it is called a significant bit or a significant digit? MSD, significant digit, let us consider. And the rightmost, so this is the leftmost digit. Leftmost digit. And coming to the rightmost digit. Rightmost digit is also known as LSD. LSD means least significant digit. So for example, we have a decimal number, for example 109. Okay, so here I said this is LSD and this is MSD. Why I can call it as MSD and LSD? Because if I change this value from 9 to 7, so what is the new value I can get? 107. Previously it was 109 and now it is 107. So there is no much change when we change the rightmost digit. Rightmost digit, the value of the number will change slightly. For example, if I make MSB as 7, so then what is the value? 707, right? So that means if I change the MSB, that is leftmost digit, the value of the number is going to be changed significantly. So that is why the leftmost digit is known as most significant digit, whereas the rightmost digit is known as left significant digit. So in any of the number system, always you remember the leftmost digit is called as MSD and rightmost digit is known as LSD. So here octal number, so it is having powers of 8. Again, octal point to the right of octal point, the positional weights positions will be starting from 0, 1, 2, 3 and so on. And to the to the right of octal point, it indicates the fractional part. Again, the positions will be starting from -1, -2, -3 and so on. So here, this is a valid octal number. Whereas, so I can represent this as base 8. Whereas 679, this is not a valid octal number. This is not a valid octal number because it includes 9 here, where 9 is not at all present in the symbols of octal number system. So that is why we cannot consider this as a octal number. Even if I have 82, is this an octal number? No, again this is not an octal number because it includes 8. Only the symbols allowed in octal number system are 0 to 7. Now coming to the next number system, hexadecimal number system. So in hexadecimal number system, actually we can hexa means the base of this hexadecimal number system is 16. So as the base of this number system is 16, what are the symbols that we can have in a hexadecimal number system? 0 to r-1, that is 0 to 15. 0 to 15. So here 0 to 9 are represented as usual, whereas A to, that is 10 to 15 are represented with capital letters A to F. A to F. So that means A is represented with 10 and capital B is represented with 11, C is represented with 12, D is represented with 13, E 14 and F 15. So that means totally how many symbols we have? 0 to 9, total 10. A, that is A is 10, A is 11, B 12, C 13, D 14, E15 and F16. Totally 16 symbols we have. Those are 0 to 9 and A to F. And this is also called as base 16 system. And here each digit will have a positional weight in the powers of 16. So again, before the point, the positional weights will be powers of 16 starting from 0 to 1 to 0 to n minus 1, whereas in the left side to the right side of point, the weights will start from again, the positions will start from -1, -2 and so on. So here example of hexadecimal number is 1A05. Even we can also consider ABC as an hexadecimal number. Even 789 is also considered to be an hexadecimal number, because 789 are also the symbols of hexadecimal number system, and ABC are also the symbols of hexadecimal number system. So this is an example of hexadecimal number system. Now, conversion. Okay, so what do you mean by conversion? Okay, so if the decimal number contains both integer part and fractional part, that convert both the parts of decimal into the other base individually. So how to convert numbers from one number system to the other number system, and why to convert a number from one number system to the other number system. So in order to reduce the storage, that is space required for storage of data, we are going for the conversion. And also we can have, based on the application, we can have different types of numbers. So that is why we are going to learn about the conversions of number system. So how to convert decimal number into its equivalent number of any base. So I want to convert a decimal number is there. So why we need to convert actually? So here actually decimal number is consisting of 0 to 9, where the computer can understand only two symbols, because the computer is a digital device, digital system. So that means here we can have only 0 and 1. That only can be understood by the computer. So I want to convert the decimal data into zeros and ones. So how to convert a decimal number into any base? Okay, so I can convert a decimal number into binary, or I can also convert it into octal or hexadecimal. Even not only binary, octal, hexadecimal, we can also have any number with any base that may be, the radix may be either 4 or 5 or 6 or 7. So based on the radix, we can have that many number of symbols in that, so that we can perform some operations. So do the division of integer part of decimal number. So now I want to convert a decimal number into any other base. So what is the procedure? Do the division of integer part. So whenever you are converting a decimal number into any base, so integer part should be converted separately and fractional part should also be converted separately. So how about the conversion of integer part? So do the successive division, and all the successive quotients with the base are noted down, and the reminders till the quotient is 0. So that means we need to successively divide the number by the by the base r, and that means into which you want to convert. So for example, I want to convert a decimal number into a binary number. So that means I want to convert base 10 to base r. So here divide the decimal number by 2 successively, and note down all the this successive division should be done till the quotient is 0, and note down all the reminders. Okay, consider the reminders in reverse order. Okay, to get the integer part of the equivalent number of base r. So what we have to do the successive division till the quotient is, till the remainder is 0, and note down all the reminders in the reverse order. That means in bottom to up approach. Okay, this means the first and last reminders denote the least significant digit and most significant digit respectively. And coming to the fractional part, how to convert it into a how to convert the fractional part of a decimal number into base r. So if for integer part we were doing the multiplication division, for fractional part we have to do the multiplication. So fractional part of decimal number and successive fractions with a base r, and note down the carry till the result is 0 or the desired number of equivalent digits is obtained. So that means now in order to convert a fractional part into any base, then we need to perform the successive multiplication. So successive multiplication, and we need to note down all the successive fractions, and we need to note down all the fractions from top to bottom approach. Now let us do one example here. So first one, binary decimal to binary conversion. Decimal to binary conversion means I want to convert it into binary, so that means r is equals to 2. Okay, so as I told you that for integer part do the division and for fractional part do the multiplication. So let us consider 123.25. This is my decimal number, or else first of all we will consider this one 123. So now I want to convert it into binary. It's equivalent binary value. It's equivalent binary value. So here, now how to do this? I want to successively divide this 123 by 2. So this is a successive division. So 2 6 are 12 and 2 1s are 2. And so how much remains here? What is the remainder? It is 1. And again do the division till the remainder becomes 0. So 2 3s are 6. So 2 30s are 60. So remainder is 1. And 2 15s are 30 and the remainder is 0. 2 7s are 14. So and the remainder is 1. And next 2 3s are 6 and the remainder is 1. 2 1s are 2 and the remainder is 1. 2 zeros are 0 and the remainder is 1. Now these are all the reminders, right? So now we need to keep track of all the reminders from bottom to up. So the first reminder is considered as MSB and the last reminder, this is considered as LSB. So what is the equivalent binary value for this decimal number 123? That is 1 2 3 4 ones 0 1 1. So this is the equivalent binary value. How can I cross check whether it is correct or not? So as positional weights here 0 1 2 3 4 5 6. So what are the positional? This is binary number, right? What are the positional weights here? 2 power 6 into 1 plus 2 power 5 into 1 plus 2 power 4 into 1 plus 2 power 3 into 1 plus 0 into anything, it is 0 plus 1 into 2 power 1 plus 0. So how much? 2 power 6 is 64 plus 32 plus 16 plus 8 plus 0 plus 2 plus 0. So if I add this, all this is 96 plus 112 plus 8 120. Sorry, it is 1, right? Into 2 power 0. So 2 power 0, this 1. So 120 plus 2, 122 plus 1, 123. So this is the decimal equivalent. So this is cross verification, not needed. Just I am saying whether it is correct or not. You can also cross check like this using positional weights. Now coming to the example, let us consider 123.625 we have. This is my decimal number. I want to convert it into binary. So already we have, I told you that we have to do separately for integer and fractional. Already we have done for the 123. What is the binary equivalent of 123? 4 ones 0 1 1, right? Now I want to take the fractional part 0.625. So for converting this into binary, I have to multiply this one by 2 in successive. So what is the multiplication of 0.625 into 2? So 2 into 5, that is 10. So 0.625 into 2. So 2 5s are 10, 2 2s are 4, it is 5. And 2 6s are 12, so it is 2 and 1.25. So it is 1.25. So take the integer part out. This is out. 1 is taken out And now the remaining number you have to take 0.25 into 2. 0.25 should be again multiplied by 2. So now what it becomes, 0.25 into 2, it is 0.5. So what is the integer part of this one? 0. Now what is the remaining number? 0.5 into 2, which is 1.0. Now 1 is taken out. 1. And here 0 into 2, 0. So again you will get the same thing. Now you keep track of all the reminders from bottom to up. So now what will be the binary equivalent of this one? 0.25 can be represented in binary as 0.101. So that means the total binary equivalent of 123.625 can be 1111011.101. You can even verify with positional weights method. You will get the same number. So this is decimal and this is binary. That is how you can convert it into binary. So again, now you want to convert a decimal number into octal. So what is the required base? That is R. R is equals to 8. So what we need to do? We need to convert it into octal. So now I am taking an example. 123 is my decimal number. I want to convert it into its equivalent octal number. So what we need to do? We need to use the perform the division operation. So by 8. So 2 8 ones are 8, and then 4 remains. 8 5s are 4, 3. Okay. Next, 8 ones are 8. So how much is the remaining thing? 15 minus 8 is 7. So can I divide this one? 0 and 1. So that is 173 is the octal number for the given decimal number. So the decimal number 123 can be represented as 173 in octal. So you can verify it. So how can I verify it? Positional weights are, so 8 power 2 into 1 plus 7 into 8 power 1 plus 3 into 8 power 0. So how much? 64 plus 7 into 8. 7 into 8, this is 56 plus 8. Sorry, not 8, 3. So how much it is? 64, 70 plus 120, 120 plus 3, 123. So like that also you can cross verify. Actually this is not needed. I am just verifying whether this is correct or not. So if I add all this, I'll get the 123. So the similar fraction. So how to convert this into octal? 625. This is a decimal number. I want to convert it into its equivalent octal number. So how to convert this? So again, already we have done for 123. What is the equivalent octal number for 123? 173 is a octal number. Now take the fractional part. Now how to do it? Successive multiplication by 8. So successive 0.625 into 8. 8 5s are 40. So 8 2s are 16. 16 plus 4, 20. So it is 2. 8 6 are 48 plus 2, that is 50. Okay. So this one 5.0. 5.0. 5, so 5 you take it out. So 5. So 0.0 you will get. It is 0. So that means here 0.625 can be converted into octal like 0.5 in octal. So now 123.625 can be converted into octal by 173.5. This is the octal. So already we have done this. How much we have got? 123 plus 5 divided 5 into what is the positional weight? Minus 1, right? So minus 1 means I can write it as 5 into 8 to the power of minus 1. That is 1 by 8. Okay. 123 plus 5 by 8. Then I will get it as 123.625. This is the answer here. So that means whatever the thing that we have got is correct on. So next, decimal to hexadecimal. So what we need to do? Now, as the previous cases, whenever you are converting a decimal number into binary, you are multiplying and dividing by 2. When you are converting a decimal decimal number into octal, you were dividing and multiplying by 8. Now you want to convert a decimal number into hexadecimal. What is the radix of hexadecimal number system? That is r is equals to 16. Now successive multiplication and division should be done by 16. So for example, let us consider ABC is my hexadecimal number. Sorry. For example, my decimal number is 123. Okay. So now I want to convert it into hexadecimal. So what I should do? I should divide 123 successively by 16. Okay. So here 16, 16, okay. 16 6 16 6 112. 123 minus 112. How much I'll get? 1, and this one is 1. 11. So how can I represent this 11? I want hexadecimal. 11 is represented in hexadecimal number system as B, where A is 10, A is equals to 10, B is equals to 11, C is 12, D is 13, and E is 14, F is 15. These things you have to keep it in mind. So as we have got the remainder as 11, so I should represent it in the hexadecimal form as B. Now again 16 zeros are, so 6. So here now I need to keep the track of these reminders from bottom to up. This is my MSB and this is my LSB. So that is 6B is my hexadecimal number for the decimal number, that is 123. So now how can I cross verify it? 6 into 16 to the power of 1 plus 11 into 16 to the power of 0. 6 16s are 6 16 6 are, so 36, 6 ones are 6, that is 96. 96 plus 11. 96 plus 11. So how much I'll get? Sorry, it is 7, I think. It is 7. 16 sevens are 112. 123 minus 112 will get 11. So 16 into 7. 7 6 are 42. Okay. 7 6 are 42. And 7 ones are 7. 11. Okay. So 112 plus 11. So how much I'll get? 123. So this is correct only. Okay. So like that, even you can convert 123.625. This is a decimal number. I want to convert it into hexadecimal. So what should we do? 0.625 into 16. 0.625 into 16. 16 5s are 80. 16 2s are 32. 32 plus 8, 40. Okay. 16 6s are 96. 96 plus 4, 100. 96 plus 4, 96 plus 4, 100. So 0 here and 10 here. So 10 is nothing but A. So that is here what you'll get? A.0. So you take A out and 0 here. So again 0 into something 0. So only A. That is 123.625. It is a decimal number that can be converted into hexadecimal as 7B.A. This is the equivalent hexadecimal number for the given. This is 7. I forgot to change it. This is 7. 7 into 16 is 112. This is 112 plus 1. So 123. And here the fractional part. So that means the number of decimal number system can be converted into any other number system of base R is done. The integer part can be converted into base R by the successive division of the decimal number by R of the resulting number system. Successive division means the division should be done until the remainder is 0, and we need to keep track of the reminders from bottom to up. That means the last remainder is considered as MSB and the first remainder is considered as LSB. Whereas the fractional part can be converted into the fractional part of a decimal number can be converted into any number system of base R with the help of successive multiplication. So this successive multiplication can be done by the resulting base r. And here the successive multiplication should be done again till the integer part becomes 0, or else we require we can stop the successive multiplication. In some cases the fractional part may not be 0. So in such kind of cases, we can terminate the successive multiplication after the required number of digits. So for example, 4 digits are enough for me. So I can stop after 4 iteration of successive multiplication by r. So like that, you can perform the successive multiplication to convert the fractional part into any base number system. So, and the integer part can be converted using successive division. So this is about the number base conversions. So that is only from decimal to any number system that we can convert. And the remaining number base conversions we'll be looking in the next class. So that's all for this lecture. I hope it is clear. So in this lecture, we have seen about what is a signal, what is an analog signal, digital signal, and what do you mean by digital electronics, and what is a number system, and what are the various types of number systems we have, and how to convert a decimal number into any other number systems. Okay, and for the remaining conversions, we'll discuss in the next class. That's all for this lecture. Thank you one and all.
Like, share and subscribe. Hit the bell icon for more updates.